In 1972, when the Pioneer 10 spacecraft departed Earth carrying its famous golden plaque, the designers made an assumption that seemed perfectly reasonable at the time. They assumed that whoever found that probe would recognize water as something special, something rare, something worth depicting with a careful diagram showing hydrogen and oxygen atoms bonded together. That assumption was half right. Water is special, but as we've learned in the decades since, it is anything but rare. The universe, it turns out, is absolutely soaked, and that revelation changes everything we thought we knew about our place in the cosmos and the possibility of life beyond Earth. Let's start with why water matters at all. Of all the molecules that exist in the universe, and there are millions upon millions of possible combinations of atoms that could theoretically form, H2O occupies a position of unique importance. Not because it's particularly complex, quite the opposite. It's one of the simplest stable molecules you can make. Two hydrogen atoms, the most abundant element in the universe, bonded to one oxygen atom, the third most abundant element. Simple. Ubiquitous. And yet, despite this simplicity, or perhaps because of it, water possesses a collection of properties so unusual, so perfectly suited to the emergence and sustenance of life, that it's difficult to imagine biology as we know it arising without it. The molecule itself is deceptively simple-looking. One oxygen atom flanked by two hydrogen atoms at an angle of about 4.5 degrees. But that angle, that specific geometric arrangement, creates something called polarity. The oxygen atom hoards electrons more aggressively than the hydrogen atoms do, which means one end of the molecule carries a slight negative charge, while the other end carries a slight positive charge. This makes water a polar molecule, and that polarity is responsible for almost everything interesting that water does. Polar molecules are exceptionally good at dissolving other substances. They surround ions and pull them apart. They interfere with the bonds holding other molecules together. They create a medium in which chemical reactions can occur with far greater ease and diversity than in almost any other substance. Life, as we understand it, is chemistry. Complex, self-sustaining, self-replicating chemistry. And chemistry needs a place to happen. Water is that place. But the strangeness of water doesn't end with polarity. Consider ice. In almost every other substance known to exist, the solid form is denser than the liquid form. Freeze something and it sinks. This makes intuitive sense. Pack molecules together in a rigid structure and they should occupy less space. But water doesn't obey this rule. Ice floats. When water freezes, it expands, becoming less dense than its liquid form. This is bizarre. This is, in fact, almost unique in nature. And it's also essential for life because if ice sank, every body of water on Earth would freeze from the bottom up. Lakes and oceans would become solid blocks of ice with perhaps a thin layer of liquid on top during summer. Instead, ice forms on the surface, insulating the liquid water below, allowing aquatic life to survive through frozen winters. This one anomaly, this strange density inversion, has shaped the entire history of life on Earth. Then there's surface tension. Water molecules are attracted to each other, those polar charges creating weak bonds called hydrogen bonds between neighboring molecules. This attraction is strong enough that water resists being pulled apart. It clings to itself with a cohesion that allows insects to walk on its surface, allows plants to pull water up from roots to leaves through capillary action, allows cells to maintain their internal structure. Surface tension might sound like a minor curiosity, but it's a fundamental enabler of biological processes. Water also has an unusually high heat capacity. It takes a lot of energy to change the temperature of water. This means bodies of water moderate climate, preventing extreme temperature swings. It means organisms made primarily of water, which is to say all organisms we've ever encountered don't overheat or freeze as easily as they would if they were made of almost anything else. Water is a thermal buffer, a climate regulator, a temperature stabilizer. For most of human history, we assumed all of this was academic. Yes, water was essential for life, but water was also rare. We had it here on Earth, and as far as anyone could tell, nowhere else. The Moon was a desiccated rock, Mars was a frozen desert, Venus was a scorched hellscape, Mercury was an airless cinder. The asteroids were rubble. The outer planets were gas giants with no solid surface. Water, liquid water especially, was Earth's gift, Earth's uniqueness, perhaps Earth's curse in rendering us lonely in a dry cosmos. That belief began to crack in 1998. The Lunar Prospector spacecraft, a small probe about the size of a washing machine, was orbiting the Moon and mapping its surface composition using a neutron spectrometer. The instrument detected something peculiar in the permanently shadowed craters near the lunar poles. The signature of hydrogen. Not just traces, but significant quantities. Hydrogen in the form of water ice, hiding in the darkness. The Moon, that ancient symbol of airless desolation, that barren companion we'd walked upon and sampled and analyzed for decades, was not entirely dry after all. The discovery was met with skepticism. Maybe it was a false positive. Maybe the instrument was malfunctioning. Maybe it was detecting something else entirely. So, NASA decided to be sure. In 2009, they crashed a spent rocket stage into one of those permanently shadowed craters, a place called Cabeus near the lunar South Pole. The impact was observed by a trailing spacecraft called L-CROSS, the Lunar Crater Observation and Sensing Satellite, which flew through the debris plume kicked up by the collision. The spectrometers aboard L-CROSS analyzed the material ejected from the impact site. Water. Unambiguous, confirmed, actual water ice. Not just traces, but a concentration of about 5% by mass in the ejected material. The Moon, dead and dry for 4.5 billion years, had been quietly hoarding water in its coldest, darkest corners. These permanently shadowed regions never see sunlight. They are cold traps where temperatures hover around 40 Kelvin, cold enough that water ice, once deposited there by comet impacts or created by interactions between solar wind and lunar soil, simply stays put. It doesn't sublimate. It doesn't go anywhere. It accumulates. If the Moon has water, what about Mercury? Mercury, the closest planet to the Sun, tidally locked in a slow rotation that bakes its sunlit side to temperatures exceeding 700 Kelvin. Surely Mercury, of all places, would be bone dry. And yet, radar observations from Earth in the early 1990s detected bright patches near Mercury's poles. Patches that looked suspiciously like ice. This seemed absurd. Mercury's poles, however, are tilted only slightly with respect to its orbit, which means some craters near the poles, much like on the Moon, are permanently shadowed. NASA's Messenger spacecraft, which orbited Mercury from 2011 to 2015, confirmed it. Water ice, possibly mixed with a darker organic material hiding in the shadows. Billions of tons of it. On Mercury. The closest planet to the Sun is hoarding frozen water in its polar craters, shielded from the Sun's fury by nothing more than topography. And then there's Mars. Mars has always occupied a special place in humanity's imagination regarding water. In the late 19th and early 20th centuries, astronomers like Percival Lowell convinced themselves they could see canals on Mars, straight lines crisscrossing the surface, which they interpreted as evidence of an advanced civilization desperately irrigating a dying world. The canals were illusions, artifacts of the human brain's tendency to see patterns, but the dream of Martian water persisted. As spacecraft began visiting Mars in the 1960s and 70s, that dream seemed to evaporate along with any hope of finding life. Mars was cold, dry, its atmosphere thin and toxic. The Viking landers in 1976 searched for organic molecules in the Martian soil and found nothing. Mars, it seemed, was dead, but then we started looking more carefully. The Mars Odyssey orbiter, launched in 2001, carried a neutron spectrometer similar to the one that found water on the Moon. It detected vast quantities of hydrogen beneath the Martian surface, particularly at high latitudes. Hydrogen, again, in the form of water ice. Not just traces, but huge reserves. The Phoenix lander, which touched down in the Martian Arctic in 2008, confirmed this directly. It dug a small trench in the soil and photographed bright white material beneath the surface. Over the course of several days, that white material sublimated, vanishing into the thin Martian atmosphere. It was water ice, just centimeters below the surface, in concentrations exceeding 80% by volume in some areas. Mars wasn't dry, Mars was frozen. The story gets more complicated and more interesting when we consider Mars's past. The planet's surface is covered in features that are difficult to explain without liquid water. There are valleys that look like they were carved by rivers. There are fan-shaped deposits that look like ancient deltas where rivers emptied into lakes or seas. There are minerals detected by orbiting spectrometers that only form in the presence of liquid water. Clay minerals, sulfates, carbonates. The northern hemisphere of Mars is significantly lower in elevation than the southern hemisphere, and some scientists believe this northern lowland was once filled with an ocean. Not a small lake, but an ocean covering a third of the planet's surface. The evidence is compelling but not conclusive. Mars, it seems, was once a very different place. Warmer, wetter, perhaps habitable. What happened? Mars lost its magnetic field, probably due to its core cooling and solidifying. Without a magnetic field to shield it, the solar wind began stripping away the Martian atmosphere. With less atmosphere, the greenhouse effect weakened, temperatures dropped, and any liquid water on the surface froze or evaporated into space. Some of it sank into the ground, becoming permafrost. Some of it migrated to the poles, forming ice caps. The polar ice caps of Mars are a mixture of water ice and frozen carbon dioxide, and they're huge. The northern ice cap, if melted, would cover the entire planet to a depth of several meters. Mars didn't lose its water. It just locked it away. Even today, liquid water might occasionally appear on Mars. There are features called recurring slope lineae, dark streaks that appear on Martian slopes during warm seasons and fade during cold seasons. They look like they could be caused by briny water seeping out of the ground, flowing downhill, and then evaporating or freezing. The evidence is tantalizing but ambiguous. Some studies suggest the streaks are just dry sand avalanches triggered by thermal expansion. Others argue that salts in the Martian soil could lower the freezing point of water enough to allow it to remain liquid, at least temporarily, in certain conditions. The debate continues, but the possibility that liquid water, even in tiny, transient amounts, exists on Mars today is difficult to dismiss entirely. Now, let's travel to the asteroid belt, that collection of rocky rubble orbiting the Sun between Mars and Jupiter. For a long time, asteroids were thought to be dry remnants of the early solar system, leftover building blocks that never coalesced into a planet. Some of them are dry, some of them are metallic, but many of them, especially in the outer regions of the belt, contain water. Not liquid water, obviously, but water chemically bound into minerals. These are called hydrated minerals, and their presence tells us something important. It tells us that water was present when these asteroids formed, that it was incorporated into their structure from the very beginning. Then there's Ceres. Ceres is the largest object in the asteroid belt, massive enough that its own gravity has pulled it into a roughly spherical shape, which technically makes it a dwarf planet. NASA's Dawn spacecraft orbited Ceres from 2015 to 2018, and what it found was astonishing. Bright spots in a crater called Okator, bright enough to be seen from Earth with a good telescope. At first, astronomers speculated these might be patches of ice. The truth turned out to be more interesting. They're salt deposits, sodium carbonate left behind by briny water that had erupted from beneath the surface and then evaporated. Ceres has, or at least had, a subsurface ocean. A dwarf planet in the asteroid belt, only 940 kilometers in diameter, harboring liquid water beneath its icy crust. Dawn's instruments detected variations in Ceres's gravitational field that are consistent with a layer of liquid or partially liquid material beneath the surface. The ocean might still be there, kept liquid by residual heat from radioactive decay in Ceres's interior. This has profound implications. If Ceres has an ocean, how many other asteroids might have had oceans in the past? How many might still have them? The asteroid belt, once dismissed as a collection of dry rocks, is starting to look like it might have been, and might still be, a much more dynamic and watery place than we ever imagined. And here's where things get really interesting. There's a theory, well supported by isotopic evidence, that Earth's oceans didn't originate on Earth. When our planet first formed, it was a molten hellscape. Any water present would have evaporated into space. So, where did our oceans come from? The leading hypothesis is that they were delivered by asteroids and comets during a period called the Late Heavy Bombardment, roughly 4 billion years ago. Asteroids from the outer belt, rich in hydrated minerals, smashed into the young Earth and released their water. Comets, essentially dirty snowballs from the outer solar system, did the same. Over millions of years, enough water accumulated to fill the ocean basins. Earth's water, the water that makes up your body, the water that falls as rain and fills rivers and sustains life, might not be native to Earth at all. It might have come from the asteroid belt. It might have come from even farther out. We are, quite literally, made of stardust and asteroid water. Finally, let's talk about Venus. Venus is often described as Earth's twin, because the two planets are similar in size and mass. But Venus is no twin of Earth. It's a cautionary tale. The surface temperature on Venus is around 740 Kelvin, hot enough to melt lead. The atmospheric pressure is 90 times that of Earth, equivalent to being a kilometer underwater. The atmosphere is mostly carbon dioxide with clouds of sulfuric acid. Nothing we would recognize as life could survive there. And yet, Venus might not have always been this way. Computer models suggest that billions of years ago, Venus might have been temperate. It might have had liquid water oceans. It orbits closer to the Sun than Earth does, but not so much closer that liquid water would have been impossible. What happened was a runaway greenhouse effect. Venus's oceans evaporated, water vapor is a greenhouse gas, which caused more warming, which caused more evaporation, which caused more warming, until the entire planet became the oven it is today. The water didn't just vanish. Some of it was broken apart by ultraviolet radiation from the sun. The hydrogen escaped into space and the oxygen reacted with rocks on the surface. But some water remains. Venus's atmosphere contains trace amounts of water vapor, not much, but it's there. And in 2020, astronomers announced the detection of phosphine in Venus's atmosphere. Phosphine is a molecule that, on Earth, is primarily produced by biological processes. The announcement caused a sensation. Could there be life in the clouds of Venus, floating in the relatively temperate upper atmosphere, far above the hellish surface? The phosphine detection has been questioned, reanalyzed, debated, and largely retracted. Follow-up observations failed to confirm it, or found much lower concentrations than initially reported. It might have been a false positive, an artifact of data processing. But the episode highlights something important. Even Venus, the most hostile planet in the inner solar system, a world that represents the worst-case scenario for climate change, still retains traces of water, still retains the possibility, however remote, of environments where chemistry interesting enough to be called life might occur. Water, it turns out, is harder to get rid of than we thought. And if it's everywhere we've looked so far, from the Moon to Mercury to Mars to asteroids to Venus, then maybe, just maybe, we need to start thinking of water not as Earth's unique treasure, but as the universe's most common and most important molecule. And if water is everywhere, and life requires water, then perhaps we've been looking at the question of life in the universe entirely wrong. Perhaps the question isn't whether life exists elsewhere. Perhaps the question is, where doesn't it exist? In 1610, Galileo Galilei pointed his primitive telescope at Jupiter and discovered 4 points of light orbiting the giant planet. He had found the first moons known to orbit a body other than Earth, a discovery that helped dismantle the geocentric model of the universe. He could not have known, could not have even imagined, that those 4 moons, Io, Europa, Ganymede, and Callisto, would centuries later become the most promising places in the entire solar system to search for life beyond Earth. Not because of what's on their surfaces, but because of what's hidden beneath. 3 of those 4 moons harbor oceans. Not ancient, dried-up ocean basins like Mars. Not frozen deposits of water ice like the Moon. Actual liquid water oceans, right now, larger and deeper than all of Earth's oceans combined. And the most tantalizing of them all is Europa. Europa is the 6th closest moon to Jupiter, and the smallest of the 4 Galilean satellites, only slightly smaller than Earth's moon. For most of history, it was just another point of light in the Jovian system, interesting primarily for its orbital mechanics and little else. That changed when the Voyager probes flew past Jupiter in 1979 and sent back the first close-up images of Europa's surface. The Moon looked like a cracked eggshell. Its surface was remarkably smooth, almost no impact craters, which immediately told scientists something strange was happening. Impact craters accumulate over time. They're the scars of billions of years of asteroid and comet bombardments. A surface without craters is a young surface, geologically speaking. Something was erasing Europa's craters, resurfacing the Moon, keeping it fresh. The leading hypothesis was ice. Europa's surface appeared to be a shell of water ice, and that shell was constantly renewing itself through some process that wasn't yet understood. But the real revelation came from the Galileo spacecraft, which orbited Jupiter from 1995 to 2003 and made multiple close flybys of Europa. Galileo carried a magnetometer, an instrument designed to measure magnetic fields, and when it flew past Europa, it detected something unexpected. Europa has no magnetic field of its own. Its small size and presumed cold interior make that impossible. But Galileo detected an induced magnetic field. This happens when a conducting material moves through an external magnetic field, in this case, Jupiter's powerful magnetosphere. The conducting material creates its own secondary magnetic field in response. The question was, what conducting material? Europa's surface is ice, which doesn't conduct electricity. Rock doesn't conduct well either, but salt water does. Salt water is an excellent conductor. The magnetic field readings suggested that somewhere beneath Europa's icy shell, there was a global layer of liquid salt water, an ocean. The implications of this were staggering. Galileo's data, combined with models of Europa's interior structure, painted a picture of a moon with a solid rocky core, surrounded by a liquid water ocean, capped by a shell of ice. The ice shell's thickness has been the subject of intense debate. Estimates range from as thin as 15 kilometers to as thick as 25 kilometers, possibly more in some regions, possibly less in others. Beneath that shell, the ocean is thought to be between 60 and 150 kilometers deep. For comparison, the deepest point in Earth's oceans, the Mariana Trench, is about 11 kilometers deep. Europa's ocean, if the estimates are correct, could contain more liquid, water than all of Earth's oceans combined. And it's all hidden beneath an icy crust on a moon that's only 3,100 kilometers in diameter. But how do we know the ice shell's thickness? We don't, not precisely. The estimates come from a combination of observations and modeling. The surface of Europa is covered in features that provide clues. There are regions called chaos terrain, jumbled blocks of ice that look like they've been broken apart, rotated, and refrozen. These suggest that the ice shell might be relatively thin in some places, thin enough that warmer, softer ice or even liquid water from below can push upward, disrupting the surface. There are also features called lenticulae, small dome-like structures that could be formed by blobs of warm ice rising from below, like a lava lamp, deforming the surface before cooling and solidifying. And then there are the lineae, long linear cracks and ridges that crisscross Europa's surface like a chaotic road map. The lineae are some of the most striking features on Europa. Some of them stretch for thousands of kilometers. They appear to be fractures in the ice shell, caused by tidal stresses. Here's where things get interesting. Europa orbits Jupiter in an elliptical path, and it's locked in orbital resonance with two other moons, Io and Ganymede. This resonance prevents Europa's orbit from becoming perfectly circular, which means the distance between Europa and Jupiter varies slightly over the course of each orbit. When Europa is closer to Jupiter, the planet's gravity pulls more strongly on the Moon, deforming it, stretching it. When Europa is farther away, the pull weakens and the Moon relaxes. This constant flexing generates heat through friction, a process called tidal heating. It's the same process that keeps Io, the innermost Galilean moon, volcanically active. On Europa, tidal heating is strong enough to keep the subsurface ocean liquid, despite the moon being so far from the sun that surface temperatures hover around 110 Kelvin. Tidal heating also drives the geological activity that creates Europa's surface features. The lineae are thought to form when tidal stresses crack the ice shell, and in some cases liquid water or slushy ice from below might erupt onto the surface, freezing and creating the ridges we see. Some of the lineae are dark, others are bright, suggesting different compositions or different ages. The fact that Europa's surface is so young, perhaps only 40 to 90 million years old based on crater counts, means the ice shell is constantly being recycled. Material from the surface is being pulled down into the ocean, and material from the ocean is being pushed up to the surface. This exchange is crucial because it means Europa's ocean is not isolated from the outside universe. If there's life in that ocean, evidence of it might be accessible on the surface or even ejected into space. Which brings us to the plumes. In 2012, astronomers using the Hubble Space Telescope reported detecting water vapor above Europa's south pole. The observations suggested that Europa was venting plumes of water vapor into space, much like the geysers on Enceladus, one of Saturn's moons. If true, this was huge. It meant we wouldn't have to drill through kilometers of ice to sample Europa's ocean. We could just fly through the plumes and analyze them. But the plumes have been maddeningly difficult to confirm. Follow-up observations sometimes see them, sometimes don't. They appear to be intermittent, possibly linked to Europa's position in its orbit around Jupiter, erupting when tidal stresses are greatest. In 2016, Hubble detected what looked like a plume again in a different location. In 2018, a reanalysis of old Galileo data suggested the spacecraft might have flown through a plume during a close flyby in 1997, detecting a localized increase in the density of charged particles. The evidence is mounting, but it's not conclusive. Europa might be venting water into space, or it might not. We won't know for certain until we send a dedicated mission to investigate. Fortunately, that mission is on its way. The Europa Clipper spacecraft launched in 2024 and will arrive at Jupiter in 2030. One of its primary objectives is to confirm the existence of the plumes and, if possible, fly through them to sample their composition. Now, let's talk about Ganymede. Ganymede is the largest moon in the entire solar system, bigger than the planet Mercury, and it's the only moon known to have its own intrinsic magnetic field. This magnetic field was discovered by Galileo in the 1990s and immediately raised questions. Why does Ganymede have a magnetic field when none of the other Galilean moons do? The answer likely lies in Ganymede's size. It's large enough that its interior might still retain enough heat for a partially molten convecting core, which could generate a dynamo magnetic field. But there was another mystery. When Hubble observed Ganymede's auroras, the glowing ribbons of light caused by charged particles interacting with the moon's magnetic field, astronomers noticed something odd. The auroras rocked back and forth in a predictable pattern. Auroras are sensitive to magnetic fields. If Ganymede's magnetic field were the only field at play, the auroras would behave one way. But if there were a secondary magnetic field, an induced field like the one detected at Europa, it would alter the behavior of the auroras. By carefully analyzing the rocking motion of Ganymede's auroras, scientists concluded that there must be a conducting layer beneath the surface. Again, salt water. Ganymede has a subsurface ocean. But Ganymede's ocean is more complicated than Europa's. Models suggest Ganymede's interior is structured like a club sandwich, multiple layers of ice and water stacked on top of each other. There's the rocky core, then a layer of high-pressure ice, then an ocean, then another layer of ice, then possibly another ocean, and finally the icy crust we see on the surface. This multi-layered structure exists because of the immense pressures in Ganymede's interior. At certain depths, water freezes into exotic forms of ice that are denser than liquid water, so they sink. The ocean or oceans inside Ganymede are thought to be sandwiched between layers of different types of ice. This makes Ganymede less exciting than Europa from an astrobiological perspective. The ocean is buried deep, possibly 150 kilometers or more beneath the surface. It's isolated, cut off from the surface by layers of ice that don't seem to be as geologically active as Europa's shell. There's less tidal heating because Ganymede, while in orbital resonance with Europa and Io, experiences less flexing. Less heating means less energy to drive chemical reactions, less circulation in the ocean, less interaction between water and rock. Interaction between water and rock is important because it's one of the ways that essential elements and chemical energy can be introduced into an ocean. On Earth, hydrothermal vents on the ocean floor, places where seawater seeps into cracks in the crust and gets heated by volcanic activity before being expelled back into the ocean, are oases of life. They're rich in minerals and chemical energy, and they support entire ecosystems that don't rely on sunlight. If Europa's ocean is in contact with its rocky mantle, it could have similar hydrothermal systems. Ganymede's ocean, buried beneath high-pressure ice, probably doesn't have that direct contact. It's colder, darker, more isolated. That doesn't mean life is impossible, but it does mean it's less likely, or at least harder to imagine. NASA's Juno spacecraft, which has been orbiting Jupiter since 2016, made a close flyby of Ganymede in 2021. Coming within 1,000 kilometers of the surface. Juno's instruments measured Ganymede's gravitational field with greater precision than ever before, and provided more data on the Moon's magnetic field. The data confirmed the subsurface ocean and refined our estimates of its depth and salinity. Juno also imaged Ganymede in remarkable detail, revealing a surface that's a patchwork of ancient dark terrain, heavily cratered and billions of years old, and younger bright terrain, crisscrossed by grooves and ridges. The bright terrain suggests that Ganymede, like Europa, has experienced geological resurfacing, though on a much slower timescale. Ganymede is geologically dead compared to Europa, but it's not completely inactive. Something is still happening beneath that icy crust. We just don't know exactly what. And then there's Callisto. Poor, neglected Callisto. The outermost of the 4 Galilean moons, Callisto is often overlooked in discussions of ocean worlds because, frankly, it's boring. Its surface is the most heavily cratered in the solar system, a record of 4.5 billion years of impacts with almost no geological activity to erase them. Callisto doesn't participate in the orbital resonance that keeps Europa and Ganymede tidally heated. It's too far from Jupiter to experience significant tidal flexing. It's cold, ancient, and dead. Or so we thought. Galileo's magnetometer detected an induced magnetic field at Callisto too. Not as strong as Europa's or Ganymede's, but it's there. Which means Callisto also has a subsurface ocean. This was a shock. Callisto shows no signs of recent geological activity. Its surface is unchanged for eons. And yet, beneath that battered crust, there's liquid water. How is this possible? The answer is probably residual heat from radioactive decay. When Callisto formed, it incorporated radioactive isotopes like uranium, thorium, and potassium into its interior. These isotopes decay over time, releasing heat. Normally, this heat would radiate away into space, and the Moon would freeze solid. But if Callisto's interior contains salts or ammonia mixed with the water, those substances act like antifreeze, lowering the freezing point and allowing liquid water to persist even at lower temperatures. Callisto's ocean is thought to be buried beneath at least 100 kilometers of ice, possibly much more. It's isolated, cold, and almost certainly devoid of the kind of chemical energy that might support life. But it exists. That's the important part. Even on a geologically dead world like Callisto, liquid water can persist for billions of years. If Callisto has an ocean, how many other moons and dwarf planets in the outer solar system might have oceans too? We used to think liquid water required a planet to orbit in the habitable zone, that narrow band around a star where temperatures are just right for water to remain liquid on the surface. The discovery of subsurface oceans on Europa, Ganymede, and Callisto obliterated that assumption. You don't need to be in the habitable zone. You don't even need to be close to the sun. You just need enough internal heat, whether from tidal flexing or radioactive decay, to keep water liquid beneath an insulating layer of ice. So let's compare Jupiter's ocean worlds. Europa gets the most attention, and for good reason. It has the thinnest ice shell, the most active surface, the strongest evidence for current geological activity, and the best prospects for habitability. Tidal heating keeps its ocean warm and drives circulation. The ice shell is thin enough that material from the ocean might reach the surface, and material from the surface might sink into the ocean, creating a chemical exchange with the outside universe. If there are hydrothermal vents on Europa's ocean floor, places where water interacts with rock and volcanic heat, then Europa has all the ingredients necessary for life as we know it. Liquid water, chemical energy, organic molecules, and time. Billions of years of time. Ganymede is less promising. Its ocean is deeper, more isolated, and receives less energy. But it's not impossible. Life, if it exists there, would have to rely on chemical energy from the slow interaction between water and rock at the base of the ocean, or perhaps on energy stored in the ice layers above. It's harder to imagine, but we've learned not to underestimate life's tenacity. Callisto is the long shot. Its ocean is almost certainly cold, isolated, and energy-poor. But even energy-poor environments on Earth can support life. Deep beneath the surface, in aquifers kilometers underground, microbes survive on the meager chemical energy provided by interactions between water and rock. Callisto's ocean might be similar. It's not a place where you'd expect a thriving ecosystem, but a few hardy microbes. Maybe. There's another factor to consider, and that's radiation. Jupiter has the most powerful magnetic field of any planet in the solar system, and it traps high-energy charged particles, creating intense radiation belts. Europa orbits deep within those belts. The surface of Europa is bombarded by radiation at levels that would be lethal to any known form of life. This is actually a problem for any potential life on Europa. If organisms exist in the ocean, they're safe, shielded by kilometers of ice. But if any biological material makes it to the surface, it's going to be sterilized by radiation almost immediately. On the other hand, that radiation breaks apart water molecules and other compounds on the surface, creating reactive chemicals like hydrogen peroxide and oxygen. If those chemicals get cycled down into the ocean, they could provide a source of chemical energy for life. Radiation might be both a curse and a blessing. Ganymede, with its own magnetic field, is somewhat shielded from Jupiter's radiation. Its surface is still irradiated, but not as severely as Europa's. Callisto, being the farthest out, receives the least radiation of the three. This might make Callisto a better place to land a spacecraft or even establish a future human base, but it also means less chemical energy being generated by radiation. There are trade-offs everywhere. Europa's ocean is the most likely to harbor life, but it's also the hardest to access and the most dangerous to explore. Ganymede's ocean is safer but less promising. Callisto's ocean is the safest and the least interesting. If we want to find life, we go to Europa. If we want to understand the diversity of ocean worlds, we study all three. And, as we'll see in the next part of this documentary, Jupiter isn't the only planet with ocean moons. Saturn has a few surprises of its own, and some of them might be even more promising than anything orbiting Jupiter. In 2005, the Cassini spacecraft was cruising through the Saturn system, methodically studying the planet's rings and moons, when it detected something strange. As it approached a small icy moon called Enceladus, Cassini's instruments registered an unexpected spike in the density of particles around it. The spacecraft was flying through a cloud of something: water vapor, ice grains, material being actively ejected from the moon's surface. This was not supposed to be happening. Enceladus is tiny, only 504 kilometers in diameter, smaller than the length of England. A moon that small should have frozen solid billions of years ago. It should be geologically dead, a cratered ice ball with nothing interesting going on. Instead, Cassini had just flown through a plume of water erupting from Enceladus's south pole. The discovery was so unexpected, so paradigm-shifting, that the mission team immediately began planning closer flybys. They had to know what was down there. Over the next several years, Cassini flew through Enceladus's plumes multiple times, sometimes passing within 25 kilometers of the surface, close enough that the spacecraft's instruments could directly sample the material being ejected. What they found was astonishing. The ice grains contained salts, sodium chloride and potassium chloride, the same salts found in Earth's oceans. They contained organic molecules, complex carbon-based compounds including some with molecular masses exceeding 200 atomic mass units. They contained silica nanoparticles, tiny grains of silicon dioxide that, based on laboratory experiments, could only have formed in water heated to at least 90 degrees Celsius in the presence of rock. In other words, the plumes weren't just water. They were salty, organically rich water that had been in contact with a rocky core and heated to temperatures where hydrothermal chemistry could occur. Enceladus wasn't just venting ice. It was venting the contents of a subsurface ocean that had all the ingredients necessary for life. The source of the plumes turned out to be a set of 4 parallel fissures near Enceladus's south pole, features that came to be known as the tiger stripes. These fissures are about 130 kilometers long, 2 kilometers wide, and they glow with infrared radiation, meaning they're warmer than the surrounding surface. The tiger stripes are actively venting water vapor and ice grains into space at speeds exceeding 400 meters per second. Some of the material falls back to the surface, creating a layer of fresh snow that makes Enceladus one of the most reflective objects in the solar system. But much of the material escapes into space, spreading out into a vast torus of ice and water vapor that encircles Saturn. This ejected material is actually the source of Saturn's E-ring, one of the planet's outermost and most diffuse rings. Enceladus is literally creating a ring around Saturn with its own ocean water. Every time you look at Saturn through a telescope and see that faint outer ring, you're seeing water from an alien ocean. But where is the ocean? Early models suggested it might be a regional sea confined to the South Polar region, sitting just a few kilometers beneath the ice. But careful analysis of Enceladus's gravity field, measured by tracking tiny variations in Cassini's radio signal as it flew past the Moon, revealed something more dramatic. The Moon's gravity was too weak for a solid interior. There had to be a layer of liquid water beneath the entire icy shell, a global ocean. Subsequent analysis of Enceladus's wobble, the way it rocks back and forth as it orbits Saturn, confirmed it. The icy shell is decoupled from the rocky core by a layer of liquid. The ocean is probably about 10 kilometers deep, sitting beneath an ice shell that varies in thickness from less than 5 kilometers at the South Pole to perhaps 30 kilometers or more elsewhere. It's a small ocean, only a fraction of the volume of Earth's oceans, but it's a global ocean on a moon barely 500 kilometers across. The heat source for Enceladus's ocean is tidal heating, the same process that keeps Europa's ocean liquid. Enceladus is locked in orbital resonance with another Saturnian moon, Dione, which prevents its orbit from becoming circular. As Enceladus moves closer to and farther from Saturn, the planet's gravity flexes the moon, generating heat through friction. The South Polar region appears to be a hot spot, perhaps because the ice shell is thinner there, allowing more heat to escape and creating a feedback loop. Heat escapes, ice melts, the shell gets thinner, more heat escapes. The tiger stripes are the surface expression of this process, cracks in the ice through which pressurized water from the ocean below is forced upward and out into space. What makes Enceladus so exciting, more exciting than Europa in many ways, is that we don't have to land on it or drill through kilometers of ice to sample the ocean. The ocean is coming to us. Cassini flew through the plumes and sampled them directly. Future missions could do the same, carrying more sophisticated instruments capable of detecting biosignatures, complex organic molecules, amino acids, maybe even cells. Enceladus is the easiest ocean world to explore because it's ejecting its secrets into space where we can reach them. And the chemistry of those plumes suggests an environment remarkably similar to hydrothermal vents on Earth's ocean floor. The silica nanoparticles, in particular, are a smoking gun. On Earth, silica particles of that size and composition form when heated seawater interacts with rock at temperatures between 90 and 200 degrees Celsius. The only place that can happen on Enceladus is at the interface between the ocean and the rocky core, where geothermal heat from the interior warms the water. Enceladus almost certainly has hydrothermal vents, places where warm, mineral-rich water percolates up from the core into the ocean, creating chemical gradients and energy sources. On Earth, hydrothermal vents are oases of life, supporting ecosystems that thrive in complete darkness, independent of sunlight, powered entirely by chemical energy. If life can exist in those conditions on Earth, why not on Enceladus? Now, let's travel to Titan. Titan is Saturn's largest moon and the second largest moon in the solar system after Ganymede. It's the only moon with a thick atmosphere, denser than Earth's, composed mostly of nitrogen with traces of methane and other hydrocarbons. The atmosphere is so thick and hazy that visible light can't penetrate it. For centuries, Titan's surface was a complete mystery. That changed in 2005 when the Huygens probe, a small lander carried to Saturn by Cassini, detached from the orbiter and plunged into Titan's atmosphere. Huygens descended through the haze for 2.5 hours, taking photographs and measurements the entire way, before landing on the surface. What it found was one of the most alien landscapes ever photographed. The surface of Titan is covered in liquid. Not water, the surface temperature is around 94 Kelvin, far too cold for liquid water. The liquid is methane and ethane, hydrocarbons that exist as gases on Earth but condense into liquids at Titan's frigid temperatures. Titan has lakes, rivers, rain, an entire hydrological cycle, but instead of water, it's methane. Cassini's radar instrument mapped Titan's surface over multiple flybys and discovered hundreds of lakes and seas, mostly clustered near the North Pole. The largest, Kraken Mare, is bigger than the Caspian Sea on Earth. These lakes fill and empty with the seasons. Titan's seasons last about 7 Earth years because Saturn takes 29 years to orbit the Sun, and the changing liquid levels create shorelines with erosion patterns and sediment deposits. There are river channels carved by liquid methane, deltas where rivers empty into lakes, and dunes made of hydrocarbon sand grains. Titan's landscape has been shaped by processes that are eerily similar to those on Earth, but with completely different chemistry. It rains on Titan. Methane evaporates from the lakes, forms clouds, and precipitates as rain. The rain carves channels, erodes hills, and flows back into the lakes, completing the cycle. It's alien hydrology, weather and erosion driven by substances that are gases on Earth, but liquids on Titan. But Titan's strangeness doesn't end with its surface. Beneath that hydrocarbon-soaked crust, Titan has a secret. Data from Cassini, particularly measurements of Titan's gravitational field and its response to Saturn's tidal forces, strongly suggest the presence of a subsurface ocean. Not methane this time, but water. Titan's interior is thought to consist of a rocky core, a liquid water ocean mixed with ammonia acting as antifreeze, and an icy shell capped by the hydrocarbon lakes and atmosphere we can see. The ocean is probably 50 to 100 kilometers beneath the surface, buried beneath an ice shell that's estimated to be at least 50 kilometers thick. The ammonia is crucial because pure water would freeze solid at Titan's internal temperatures. Ammonia lowers the freezing point, allowing the ocean to remain liquid. But ammonia also makes the ocean less hospitable to life as we know it. Ammonia is toxic to most Earth organisms, and its presence raises the question of whether life could evolve in such an environment. It's not impossible, but it's harder to imagine. There's another problem. Titan's subsurface ocean is isolated from the surface. The ice shell is thick, and there's no evidence of cryovolcanism or plumes like we see on Enceladus. The surface of Titan is rich in organic molecules. The atmosphere is constantly producing complex hydrocarbons through photochemistry driven by sunlight, and those molecules rain down onto the surface. It's a prebiotic chemist's dream, an environment full of the building blocks of life. But those molecules stay on the surface. They don't make it down to the subsurface ocean, and the ocean, buried beneath kilometers of ice, has no access to the organic richness above. If life exists on Titan, it's either in the methane lakes on the surface, which is a completely different kind of biochemistry that we can barely speculate about, or it's in the subsurface ocean, cut off from the organic bounty above, relying solely on whatever chemistry occurs at the interface between water and rock. Titan is fascinating, bizarre, and absolutely worthy of exploration. NASA's Dragonfly mission, a nuclear-powered quadcopter that will launch in 2027 and arrive at Titan in the mid-2030s, will explore the surface, sampling the organic-rich sands and searching for signs of prebiotic chemistry. But the subsurface ocean will remain out of reach, at least for now. And then there's Mimas. Mimas is a small moon of Saturn, about 400 kilometers in diameter, and it's famous for one thing. It looks like the Death Star from Star Wars. There's a giant impact crater called Herschel on one side, giving Mimas an uncanny resemblance to the fictional space station. For decades, Mimas was considered one of the least interesting moons in the solar system. Its surface is heavily cratered, ancient, showing no signs of geological activity. It's cold, dead, inert, or so everyone thought. In 2024, a team of scientists published a study based on Cassini data that stunned the planetary science community. Mimas, it turns out, has a subsurface ocean. The evidence came from careful analysis of Mimas's orbital motion and its libration, the way it wobbles as it orbits Saturn. The libration was too pronounced for a solid interior. Something inside Mimas was sloshing around, decoupling the icy shell from the rocky core. That something was liquid water. This discovery is shocking for two reasons. First, Mimas shows absolutely no surface evidence of geological activity. There are no tiger stripes, no smooth regions suggesting resurfacing, no signs of heat escaping from the interior. The surface looks billions of years old. Second, Mimas is small and orbits relatively far from Saturn, so it shouldn't be experiencing enough tidal heating to maintain a subsurface ocean. And yet, the ocean is there. Models suggest it's a relatively young ocean, possibly only a few million years old, maybe even younger. Perhaps Mimas was recently captured into an orbital resonance that generated a burst of tidal heating, melting the interior, and the ocean hasn't frozen yet. Or perhaps there's something about its interior composition, maybe a high concentration of ammonia or salts that allows liquid water to persist at lower temperatures. We don't know. What we do know is that Mimas forces us to reconsider every other small, cratered, dead-looking moon in the solar system. If Mimas has an ocean, what else are we missing? Now, let's venture to the outer reaches of the solar system, beyond Saturn, into the cold and dark where the sun is just a bright star. Neptune's largest moon, Triton, is one of the strangest objects in the solar system. It's the only large moon that orbits its planet in the opposite direction of the planet's rotation, a retrograde orbit, which strongly suggests Triton wasn't formed alongside Neptune but was captured from the Kuiper Belt. When Voyager 2 flew past Triton in 1989, it discovered a geologically active surface with very few impact craters, indicating recent resurfacing. It also discovered geysers. Nitrogen geysers erupting from the surface and carrying dark organic material into the thin atmosphere, where it fell back as streaks across the icy plains. The geysers are thought to be driven by solar heating of subsurface nitrogen ice, which vaporizes and bursts through the crust. But Triton might also have a subsurface water ocean. The evidence is circumstantial, based on models of Triton's interior and the fact that it's geologically active. If Triton was captured from the Kuiper Belt, the process of being captured would have generated enormous amounts of tidal heating, as Neptune's gravity circularized its orbit. That heat would have melted the interior, creating an ocean. Whether that ocean still exists today, billions of years later, is unknown. But Triton is a candidate, another world that might be hiding liquid water beneath its icy crust. And then there's Pluto. Yes, Pluto. When New Horizons flew past Pluto in 2015, one of the most striking features it discovered was a vast plain of smooth, nitrogen ice called Sputnik Planitia. The plain sits in a large impact basin, and it shows no impact craters, meaning it's geologically young, constantly being resurfaced by the slow convection of nitrogen ice. But Sputnik Planitia is also aligned almost exactly opposite Pluto's largest moon, Charon, a configuration that suggests a positive mass anomaly beneath the plane, something denser than the surrounding ice pulling on Charon and locking the plane into that position. The leading explanation is a subsurface ocean. Water is denser than ice, so a pocket of liquid water beneath Sputnik Planitia would create exactly the kind of mass anomaly needed to explain the alignment. Models suggest the ocean could be 100 kilometers deep, sitting beneath a shell of water ice perhaps 200 kilometers thick. The ocean is probably loaded with ammonia to keep it from freezing, and it's kept liquid by residual heat from Pluto's formation, and possibly by the decay of radioactive elements in the core. Pluto is 40 times farther from the Sun than Earth. Surface temperatures are around 40 Kelvin. It's so cold and so distant that it seems absurd to imagine liquid water there. And yet, the evidence suggests it exists. If Pluto has an ocean, then so might dozens or hundreds of other Kuiper Belt objects. The outer solar system might be full of hidden oceans, worlds we've dismissed as frozen and dead, but which harbor vast reservoirs of liquid water beneath their icy exteriors. Water ice is ubiquitous in the Kuiper Belt. Spectroscopic observations of these distant objects show the signatures of water ice on their surfaces. And if they contain radioactive elements, which is likely given they formed from the same primordial material as everything else in the solar system, then they have an internal heat source. It might not be much heat, but it doesn't take much to keep water liquid if you have a thick enough insulating layer of ice above it and enough ammonia or salts mixed in to lower the freezing point. The implications of all this are staggering. We used to think liquid water was rare, confined to Earth and maybe a few places in the inner solar system if we were lucky. We now know that liquid water is common. Europa, Ganymede, Callisto, Enceladus, Titan, Mimas, possibly Triton, possibly Pluto, possibly hundreds of Kuiper Belt objects. The solar system is full of oceans, and if our solar system is full of oceans, then other solar systems are probably full of oceans too. Exoplanets and exomoons orbiting distant stars, icy worlds far from the warmth of their suns, could harbor subsurface oceans kept liquid by tidal heating or radioactive decay. The habitable zone, that narrow band around a star where temperatures are just right for liquid water on the surface, is no longer the only place to look for life. Subsurface oceans expand the habitable real estate of the universe by orders of magnitude. Almost any moon or planet with ice and an internal heat source could have an ocean. And where there's water, there's the possibility of life. We've gone from thinking we might be alone in the solar system to realizing we're surrounded by potentially habitable environments. The question is no longer whether there are places where life could exist. The question is whether life actually exists in any of them. And that's what we'll explore in the final part of this documentary, where we'll venture beyond the solar system, examine the water we've found on exoplanets, discuss the role of comets, and grapple with the profound implications of living in a universe where water, the molecule of life, is everywhere. In 1995, astronomers discovered the first planet orbiting another Sun-like star. The planet, 51 Pegasi b, was nothing like anything in our solar system. It was a gas giant, roughly half the mass of Jupiter, but it orbited its star every 4 days at a distance closer than Mercury orbits our Sun. This should not have been possible. Gas giants were supposed to form far from their stars, where temperatures were cold enough for ice to condense. And yet, there it was. A hot Jupiter, as such planets came to be known, orbiting so close to its star that its atmosphere was being heated to over 1,000 Kelvin. The discovery of 51 Pegasi b opened the floodgates. In the decades since, astronomers have discovered over 6,000 exoplanets, and the diversity is staggering. There are super-Earths, mini-Neptunes, lava worlds, ice giants, planets orbiting binary stars, planets orbiting dead stars, planets with years that last only a few hours, and planets so far from their stars that a year takes thousands of Earth years. And on many of these worlds, we've detected water. Detecting water on a planet dozens or hundreds of light years away is not straightforward. We can't simply point a telescope at an exoplanet and see oceans or clouds. Most exoplanets are too small and too close to their bright parent stars to be directly imaged. Instead, we rely on a technique called transit spectroscopy. When a planet passes in front of its star, from our perspective, it blocks a tiny fraction of the star's light. But some of that starlight passes through the planet's atmosphere, if it has one, before reaching us. Molecules in the atmosphere absorb specific wavelengths of light, creating absorption lines in the spectrum. By analyzing those absorption lines, we can determine the chemical composition of the atmosphere. Water vapor, for instance, absorbs light at specific infrared wavelengths. If we see those absorption features in the spectrum of a transiting exoplanet, we know there's water vapor in its atmosphere. This technique has been used successfully to detect water vapor on dozens of exoplanets, but there's a catch. Most of the planets where we've confirmed water are hot Jupiters. These are gas giants with scorching atmospheres, far too hot for liquid water. The water exists as vapor mixed with hydrogen, helium, and other gases. It tells us that water is present, which is interesting, but it doesn't tell us much about habitability. And then there's another problem. Many exoplanets have cloudy or hazy atmospheres that obscure the spectral features we're looking for. The Hubble Space Telescope and other observatories have attempted to characterize the atmospheres of numerous potentially habitable exoplanets, only to find that clouds block most of the signal. It's frustrating. We know the planets are there. We know some of them might have water, but we can't confirm it because the atmospheres are opaque. The James Webb Space Telescope, launched in 2021, was supposed to change this. JWST is far more sensitive than Hubble, particularly in the infrared, and it has the capability to pierce through some of those hazy atmospheres and detect molecules that Hubble couldn't. One of its first targets was a planet called K2's 18b. This planet is about 120 light-years away, orbits a red dwarf star, and is roughly 8 times the mass of Earth. It sits within its star's habitable zone, the region where temperatures might allow liquid water to exist. Early observations suggested it might have water vapor in its atmosphere, but the data was ambiguous. In 2023, JWST observed K2 18b, and the results were tantalizing. The observations confirmed the presence of water vapor and also detected methane and carbon dioxide. But the real surprise was the potential detection of dimethyl sulfide, a molecule that, on Earth, is almost exclusively produced by biological processes, specifically by phytoplankton in the oceans. The detection of dimethyl sulfide on K2 18b has not been confirmed. The signal is weak, right at the edge of what JWST can reliably detect, and there are alternative explanations that don't involve life. But if it's real, if K2 18b's atmosphere contains dimethyl sulfide, it would be the first potential biosignature detected on an exoplanet. The implications would be staggering. K2 18b is what's known as a Hycean world, a hypothetical class of planet characterized by a hydrogen-rich atmosphere overlying a global water ocean. The term Hycean combines hydrogen and ocean. These worlds are thought to be larger than Earth but smaller than Neptune, with thick atmospheres and potentially habitable oceans beneath. The concept is controversial because we don't know if such planets can actually support life. The atmospheric pressure at the ocean surface might be crushing, the water might be too hot or too acidic, and the hydrogen atmosphere might prevent the kind of atmospheric chemistry that life relies on. But it's a possibility, and K2-18b is the leading candidate. The debate over what counts as a water world in the exoplanet catalog is ongoing. Some astronomers define a water world as any planet where water makes up a significant fraction of the total mass, perhaps 10% or more. Others require the presence of a liquid water ocean on or near the surface. The problem is that we can't directly measure water content. We can infer it from a planet's mass and radius, which tell us its average density, and from spectroscopic observations of the atmosphere. A planet with low density and water vapor in its atmosphere is probably rich in water, but we can't say for certain how much of that water is liquid, solid, or vapor. And then there's the question of habitability. A planet could have vast oceans and still be uninhabitable if the oceans are too hot, too cold, too acidic, or subjected to too much radiation. One of the most exciting exoplanet systems for the search for water worlds is TRAPPIST-1. This system, located about 40 light-years away, consists of a small red dwarf star orbited by 7 Earth-sized planets. 3 of those planets orbit within the habitable zone. When the system was discovered in 2017, it was hailed as one of the best places to search for life beyond the solar system. JWST has since observed several of the TRAPPIST-1 planets, and the results have been mixed. TRAPPIST-1b, the innermost planet, appears to have little or no atmosphere. It's too close to the star, and the stellar wind has likely stripped away any atmosphere it once had. TRAPPIST-1c also shows no signs of a thick atmosphere. But the outer planets, particularly TRAPPIST-1e, F, and G, remain intriguing. Early observations suggest they might have atmospheres, and models predict that some of them could have significant amounts of water. Whether that water is in the form of oceans, ice, or atmospheric vapor is unknown. JWST will continue to observe these planets over the coming years, and will gradually build up a clearer picture of their compositions and potential habitability. But the process is slow and painstaking. Detecting water on an exoplanet requires multiple observations, careful analysis, and ruling out alternative explanations. It's not something that happens overnight. Now let's talk about comets. Comets are often described as dirty snowballs, mixtures of water ice, frozen gases, dust, and rock left over from the formation of the solar system. They originate in 2 main regions, the Kuiper Belt, beyond Neptune, and the Oort cloud, a vast spherical shell of icy objects surrounding the solar system at distances up to 100,000 astronomical units. When a comet's orbit brings it close to the Sun, the ice begins to sublimate, creating a glowing coma and often a spectacular tail. For a long time, comets were thought to be the primary source of Earth's water. The theory went like this: Earth formed hot and dry. Any water present during its formation would have evaporated. Later, during a period called the Late Heavy Bombardment, comets from the outer solar system crashed into Earth, delivering water and organic molecules. Over millions of years, enough water accumulated to fill the oceans. But this theory ran into a problem when the European Space Agency's Rosetta mission rendezvoused with a comet called 67P Churyumov-Gerasimenko in 2014. Rosetta spent 2 years studying the comet up close, even landing a small probe called Philae on its surface. One of Rosetta's key measurements was the deuterium to hydrogen ratio in the comet's water. Deuterium is an isotope of hydrogen with an extra neutron, and its abundance relative to regular hydrogen varies depending on where and how water formed. Earth's oceans have a specific deuterium to hydrogen ratio, and if comets delivered Earth's water, their ratio should match. It doesn't. The water on 67P had a deuterium to hydrogen ratio roughly 3 times higher than Earth's oceans. This suggests that comets like 67P were not the primary source of Earth's water. So, where did Earth's water come from? The leading alternative is asteroids. Certain types of asteroids, particularly those in the outer asteroid belt, contain hydrated minerals and have deuterium to hydrogen ratios much closer to Earth's. These asteroids could have bombarded the early Earth and delivered water that was chemically similar to what we have today, but comets might still have played a role. Not all comets have high deuterium ratios. Some, particularly those originating from the Kuiper Belt rather than the Oort cloud, have ratios closer to Earth's. The truth is probably a combination. Earth's water came from both asteroids and comets, with asteroids contributing the bulk, but comets adding a smaller fraction. The debate continues, and missions like Rosetta have shown us that comets are more diverse and complicated than we thought. And then there are the interstellar comets. In 2017, astronomers detected an object passing through the solar system on a trajectory that indicated it came from another star system. The object, named Oumuamua, was highly elongated, tumbling end over end, and accelerating slightly in a way that couldn't be explained by gravity alone. Some scientists speculated it was a comet, and the acceleration was caused by outgassing as ice sublimated. Others argued it was too small and showed no visible coma or tail. The debate over what Oumuamua actually was, comet, asteroid, alien spacecraft, has not been resolved. But in 2019, a second interstellar object was detected, this one unambiguously a comet. Named Borisov, it had a visible coma and tail, and spectroscopic observations detected water vapor and cyanogen gas in its coma. Borisov's composition appeared similar to comets from our own solar system, suggesting that comet formation is a universal process. If water-rich comets are common in other star systems, and we have no reason to think they aren't, then water is being delivered to planets around other stars, just as it was delivered to Earth. The building blocks of life, water, and organic molecules are not unique to our solar system. They're everywhere. So let's step back and consider the implications. For most of human history, we assumed that life required very specific conditions. A rocky planet orbiting a sun-like star at just the right distance to have liquid water on its surface. The habitable zone. We imagined this zone as a narrow band, maybe spanning a few tens of millions of kilometers, where temperatures were neither too hot nor too cold. Planets closer to the star would be too hot, their water boiling away. Planets farther out would be too cold, their water frozen. The habitable zone was where Goldilocks lived, where everything was just right. But the discovery of subsurface oceans has obliterated this tidy picture. Europa orbits Jupiter at a distance of about 670,000 kilometers. Jupiter orbits the Sun at an average distance of 778 million kilometers, more than 5 times farther than Earth. By the traditional definition, Europa is nowhere near the habitable zone. And yet it has a liquid water ocean. So does Enceladus, orbiting Saturn at nearly 1.5 billion kilometers from the Sun. So might Pluto at 5.9 billion kilometers. The habitable zone, as we traditionally conceived it, is irrelevant for subsurface oceans. As long as a moon or planet has an internal heat source, whether from tidal heating or radioactive decay, and an insulating layer of ice, it can maintain liquid water no matter how far it is from its star. This expands the habitable real estate of the universe by orders of magnitude. Almost any icy moon or planet, anywhere in any star system, could potentially harbor a subsurface ocean. The number of potentially habitable environments in the galaxy is not in the billions, it's in the trillions. But there's a catch, and it's a big one. Life on Earth, at least the life we're most familiar with, relies on sunlight. Plants and photosynthetic bacteria use sunlight to convert carbon dioxide and water into sugars and oxygen, forming the base of nearly every food chain. Sunlight doesn't penetrate ice shells dozens of kilometers thick. If there's life in Europa's ocean or Enceladus's ocean, it can't rely on photosynthesis. It has to rely on chemosynthesis, using chemical energy instead of light energy. On Earth, chemosynthesis occurs at hydrothermal vents on the ocean floor. These are places where seawater seeps into cracks in the crust, gets heated by volcanic activity, reacts with minerals in the rock, and is expelled back into the ocean laden with chemicals like hydrogen sulfide, methane, and hydrogen. Bacteria and archaea living near these vents use those chemicals as an energy source, and they in turn support entire ecosystems of tube worms, clams, crabs, and fish. These ecosystems exist in complete darkness, kilometers below the surface, utterly independent of the sun. If life exists on Europa or Enceladus, it probably looks more like the life around hydrothermal vents than the life in a sunlit coral reef. It's microbial, slow-growing, and eking out an existence on the meager energy provided by chemical reactions. It's not impossible. It's just harder to imagine complex multicellular life evolving in such energy-poor conditions. And then there's the timeline problem. Life on Earth appeared relatively quickly, geologically speaking. The planet formed about 4.5 billion years ago, cooled enough for liquid water to exist by about 4.4 billion years ago, and the earliest evidence of life dates to at least 3.7 billion years ago, possibly earlier. That's a gap of only a few 100 million years. Life got started fast, but it took much longer for complex life to evolve. Multicellular organisms didn't appear until about 600 million years ago, and intelligent life capable of building spacecraft didn't appear until 200,000 years ago. If the same timeline applies to subsurface oceans, and there's no reason to think it wouldn't, then even if life emerges quickly in these environments, it might take billions of years to evolve into anything we'd recognize as complex. Europa's ocean has existed for billions of years. That's plenty of time for microbes to emerge and evolve. But has it been enough time for anything more? Fortunately, we won't have to wait billions of years to find out. Missions are already underway or in development to search for life in these subsurface oceans. The Europa Clipper spacecraft launched in October 2024 and will arrive at Jupiter in 2030. It won't land on Europa. The radiation environment is too harsh for a lander to survive long. Instead, Clipper will orbit Jupiter and make dozens of close flybys of Europa, coming within 25 kilometers of the surface. Its instruments will map the ice shell, measure its thickness, analyze the composition of surface materials, and search for plumes. If Europa is actively venting water into space like Enceladus, Kuiper will fly through those plumes and sample them. The spacecraft carries a mass spectrometer capable of detecting organic molecules, salts, and potentially even biosignatures. It also carries cameras with resolution high enough to see features as small as 50 centimeters across, which could reveal surface details that tell us more about the ocean below. Kuiper won't definitively prove whether life exists on Europa. That would require landing, drilling through the ice, and directly sampling the ocean. But it will tell us whether Europa has the ingredients for life and whether it's worth sending a follow-up mission to dig deeper. Then there's Dragonfly, a mission to Titan scheduled to launch in 2027 and arrive in the mid-2030s. Dragonfly is unlike any spacecraft ever sent to another world. It's a quadcopter, a drone powered by a radioactive thermal generator, and it will fly from site to site on Titan's surface, sampling the organic-rich sands, analyzing the chemistry of the methane lakes, and searching for prebiotic molecules. Titan's thick atmosphere makes flying relatively easy. The air is 4 times denser than Earth's, so Dragonfly can cover hundreds of kilometers during its mission, exploring a variety of environments. The goal is to understand Titan's chemistry and determine whether the conditions are right for life to emerge, either in the methane lakes on the surface or in the subsurface water ocean. Dragonfly won't reach the subsurface ocean. That would require drilling through tens of kilometers of ice, but it will provide crucial data on Titan's habitability. As for Enceladus, there are multiple mission proposals in various stages of development. The most ambitious would involve a spacecraft that doesn't just fly through the plumes but actually collects samples and analyzes them in detail, searching for amino acids, lipids, and other biomolecules. Some proposals even include a lander that could touch down near the tiger stripes and sample freshly erupted material. Enceladus is the easiest ocean world to explore because the ocean is coming to us. We don't need to drill. We just need to collect what's already being ejected and analyze it with instruments sensitive enough to detect signs of life. The challenge is funding. Space missions are expensive, and there are many targets competing for limited resources. But the scientific case for an Enceladus mission is strong, and it's likely that within the next few decades we'll send a dedicated mission to search for life in its plumes. And then there's the question of exoplanets. JWST will continue to observe potentially habitable worlds, searching for water vapor, oxygen, methane, and other molecules that might indicate the presence of life. The next generation of ground-based telescopes, like the extremely large telescope currently under construction in Chile, will have the resolution and sensitivity to directly image some nearby exoplanets and analyze their atmospheres in even greater detail. We're entering an era where detecting biosignatures on exoplanets is not just theoretically possible, but practically within reach. If we find water on an Earth-like exoplanet orbiting in the habitable zone of a Sun-like star, and if we detect oxygen and methane in its atmosphere, gases that on Earth are primarily produced by life, we'll have strong circumstantial evidence for extraterrestrial biology. It won't be proof. There are non-biological ways to produce those gases, but it will be compelling enough to justify follow-up missions and more detailed observations. So let's bring this all together. Water is not rare. It's one of the most common molecules in the universe. Hydrogen is everywhere. Oxygen is abundant. Put them together and you get water. It's in comets, asteroids, planets, moons, interstellar clouds, even in the atmospheres of stars. Everywhere we look, we find water. And if water is everywhere, and life as we know it requires water, then the logical conclusion is that the potential for life is everywhere too. We've gone from assuming Earth was unique, the only world with oceans, to realizing that oceans are common. We've gone from thinking the habitable zone was a narrow band around sun-like stars to realizing that habitable environments can exist almost anywhere, as long as there's liquid water and an energy source. The universe, it turns out, is far more hospitable than we ever imagined. But this raises a troubling question. If water is so common and potentially habitable environments are so abundant, then where is everybody? This is the Fermi paradox. The galaxy is old, over 13 billion years. There has been plenty of time for life to emerge, evolve, and spread. If even a tiny fraction of those trillions of potentially habitable environments actually harbor life, and if even a tiny fraction of those give rise to intelligent, spacefaring civilizations, then the galaxy should be teeming with life. We should see evidence of it everywhere. Megastructures, radio signals, probes visiting our solar system, and yet we see nothing. The silence is deafening. There are many possible explanations. Maybe life is common, but intelligence is rare. Maybe intelligence is common, but civilizations destroy themselves before they can spread. Maybe interstellar travel is harder than we think. Maybe we're looking in the wrong places or listening at the wrong frequencies. Or maybe we're the first. Maybe, in the vast expanse of the Milky Way, we're the first species to reach this level of technological development. It's statistically unlikely, but not impossible. Somebody has to be first. The abundance of water doesn't resolve the Fermi paradox, but it does make it more perplexing. The ingredients for life are everywhere. The environments where life could exist are everywhere. So why don't we see life everywhere? Perhaps the answer lies in the final step, the transition from chemistry to biology. Water is necessary, but not sufficient. You also need the right molecules, the right energy sources, the right conditions, and a lot of time. Maybe that combination is rarer than we think. Or maybe it's common, and the galaxy is full of microbial life, but complex, intelligent life is the rare exception. We won't know until we actually find life somewhere other than Earth. And when we do, when we finally confirm that we're not alone, it will be one of the most profound moments in human history. It will change everything. Our understanding of biology, our place in the universe, our sense of purpose and destiny. The discovery of life on Europa, or Enceladus, or an exoplanet dozens of light years away will not just be a scientific breakthrough. It will be a philosophical and existential reckoning. We will finally know that life is not unique to Earth, that the processes that gave rise to us have occurred elsewhere, that we are part of something much larger. And it all starts with water. The simplest molecule, the cosmic solvent, the liquid of life. Water is everywhere, and where there's water, there's hope.